Hello again, welcome to International Institute of Non-Destructive Testing. So today we are going to discuss here magnetic particle testing, the principle of magnetic particle testing. Now see, this is the bench type machine, and this is the crankshaft, and this is coil, and this is head, and that other side is tail. So we are doing head shot and coil shot in this bench type of machine. Okay, so in lesson number one, we are seeing the introduction to magnetic particle testing, objective, theory of magnetization, and magnetic material. So, introduction to magnetic particle testing, because magnetization of certain material is possible. It is possible to reveal discontinuities by using a medium iron powder having magnetic attraction. Because if in case of ferromagnetic material, if you are applying to current to that ferromagnetic material, then that material, that job, the specimen becomes a magnet. So that's why we can do magnetic particle testing of ferromagnetic material. So magnetic particle testing principle is based on north and south pole leakage, or we can say pole formation. A magnet means, we can say simple way, that is a sum of the line of force, and if there is any defect, then that line of force came out of the surface, and we can say leakage field, or we can say field leakage. And in that case we are getting north and south pole, and north and south poles we know that is dissimilar pole, and if you are applying iron particle there, then powder, that indication will be formed. And this is the simple principle of magnetic particle testing. And then we will see in details. The medium is applied to the surface of test object after or during induction of magnetic field, means while we are flowing, while we are applying current, means current is flowing, and the same time we are applying magnetic ink, or we can say iron particles. Now see, let's this see the sketch. Now this is the job, and after application of current, the job becomes a magnet. This is north pole, this is south pole, and the these are the line of force, and line of force always travel at least resistance, because in here the defect there is air, and in air there is more resistance to line of force. That's why some of the line of force came out here, and we are getting here north and south pole, and that north and south pole, that means this similar pole, and there is attraction towards iron particles. So magnetic particle testing is a relatively easy and simple test method that can be applied at various stage of manufacturing and processing operations, to ensure product reliability, by providing by means of obtaining a visual image of an indication on the surface of material. If there is any discontinuity, then indication will form on surface of material, disclosing the nature of discontinuity without impairing the material, separating acceptable and unacceptable material in accordance with predetermined standards. Now theory of magnetization. Now see here, the this is the north pole of this magnet, south pole of this magnet, and here north and south. See here, you are seeing here the line of force is in the closed form, means they are attract each other. Here is a similar pole, north pole here, again here north pole. So this is a repulsion. Means similar, dissimilar pole, north and south, there is attraction, repulsion in similar pole, north or south. They will not attract each other, they will repel each other. So an object is magnetized when part or all of its magnetic domains have their north and south pole oriented. After magnetization, after application of current in ferromagnetic material, the domain will aligned in one direction. And when domain is aligned in one direction, when domains are aligned in one direction, then we can say the job is magnetized. Okay, the ability of magnet to attract or repel is concentrated at local area called poles. Means here is pole, there is line of force is living at that area, or sometimes entering at that area. The north and south pole exhibit attraction and repulsion. So here we are going to discuss again this theory of magnetization. See, this is the domain is randomly oriented here. This condition is before magnetized or after demagnetized. Demagnetized means after testing we are removing the magnetic field, that is known as demagnetized condition. Now see here, magnetized condition, here the line of force, sorry, the domains are aligned in the direction of line of force, so we can say fully magnetized. Now see, this is the line of force. See, this line of force is leaving the job here, is going surrounding, again entering here in the pole. So leaving and entering area, we can say that is the pole, north and south poles. So these are the magnetic line of force which form a closed loop or circuit. All the line of force make up the magnetic field. Magnetic field means it is sum of line of force. So the force that attract other magnetizable material to the magnet poles is known as magnetic flux. Magnetic flux is made up of all the line of force. Means like magnetic field or magnetic flux is made up all of the line of force. Means that is based on total number of lines. If line of force are more, then magnetic flux will be more. Magnetic field will be more. So Harshow magnet will attract other magnetizable material only where the line of force leave or enter the magnet. See here, this is the we can say Harshow magnet here. See, this is line of force leaving here, so it will enter into the ferromagnetic material, again is entering into the south pole, so the circuit is completed. Now, so if any defect here we can detect. Here also you can see the line of force within the material is traveling from south to north. Is traveling from south to north, and outside the material, see here also outside, this is the within the magnet, south to north, outside the material, north to south. So here some of the line of force will came out and we're getting flux leakage. And if you are applying iron particle there, then magnetic field, the leakage field will be generated, or we can say the powder will accumulated because of leakage field. If magnet is bent into a complete loop as shown below, the magnetic field is entirely within, thus no external force. Now see, this is the circular job, and if we are applying circular magnetic field, then this line of force will not came outside. See how it's moving within the job, because this is circular magnetic field. In case of longitudinal magnetic field, it will came outside. So what about the defect if suppose appear here? So it will came out. Now, however, a crack in the circular magnet will disturb the flow of line of force and create flux leakage. See here, because because of this crack, some of the line of force will came out, and we will get the flux leakage. And if you are applying iron particles, then we are getting the indication. Now leakage field will attract magnetic particles. Leakage field and flux leakage are actual magnetic line of force that leave the part and pass through here from one pole to other pole, or the one pole to other of opposite polarity, means negative to positive or north to south. And now whenever the leakage field is forced out of the part, iron particle would be attracted, showing a indication of a discontinuity. Even some subsurface discontinuities may be detected if the leakage field is strong enough as shown below. Now here see, this is the surface defect, so many line of force will came out. So we are getting strong leakage field. But here some of the line of force is passing between defect and this outer surface. So some of the line of force will came out. So the indication will be weak because less line of force will came out of the job. Now this is the vector field, and suppose if you are applying current from this direction, and you are applying current from this direction at the same times, then we are getting the vector field, resultant field, which will moving in this direction. So that is the vector field. Now the amount of field is a combination of both this field and this field. Means if suppose this is a and this is b, then this vector will be a plus b. So this is the important parameters when we are applying two shot simultaneously, means head shot and coil shot. Then the field will be vector field. Now magnetic material. So we can only do magnetic particle testing of ferromagnetic materials. And ferromagnetic material means whenever we are applying current, the material becomes magnet. Even after removing of current, there is some residual magnetic field. And that material we can say ferromagnetic material. So if an object is placed in magnetic field, a force is exerted on it, and it is said to becomes magnetized. The intensity of magnetization depends upon the susceptibility of material to become magnetized. And this magnetization depends upon permeability of material. So permeability is different for different material. So diamagnetic metal means you have a small and negative susceptibility to magnetization, slightly repelled. This diamagnetic material, suppose if you are trying for magnetizer, so it will even it will repel, it will oppose to magnetization, or it will repel. Okay, copper, silver, gold are example of diamagnetic metals. Now paramagnetic metals means have a small and positive susceptibility to magnetization, slightly attracted. And the examples is magnesium, molybdenum, lithium, titanium are examples. And the last one is ferromagnetic metals have a large and positive susceptibility to magnetization. They have strong attraction and are able to retain their magnetization after the magnetizing current has been removed. Iron, cobalt, nickel are example of ferromagnetic material. Now, these ferromagnetic material are the only metals commonly inspected with magnetic particle testing method. So here we saw already three metals. Diamagnetic materials means even if you are trying for magnetize that diamagnetic material, it will repel. It will never accept magnetic field. That will oppose. Then paramagnetic, it will attract, it will get some little bit magnetic field, a small attraction to line of force. And ferromagnetic material have a strong attraction to line of force. And even if you are removing the current, then also there is magnetic field, residual magnetic field, and that is known as ferromagnetic metals. And these ferromagnetic metals we can do magnetic particle testing for detection of surface and near surface cracks. Now, magnetic flux means we already saw the magnetic field created because of line of force. So, magnetic flux means magnetic field, and that is sum of total number of line of force. In simple words, this total number of line of force will create magnetic field or will create magnetic flux within the job. Now, flux density is little bit the same, but depends on area. It is flux per unit area. It is not exactly same. Here the magnetic field or magnetic flux per unit area at right angle to the direction of flux. So this is generally measured in Gauss. Now right hand rule and left hand rule. Now you just see the thumbs here. Now current is flowing through thumbs direction and magnetic field is fingers direction. So in right hand rules, we are generally using the current flow theory. If we are sending current through thumbs direction, the magnetic field will be in fingers direction. So current will flow from positive to negative, and in left hand rule, electron flow theory, and we are sending electron from negative to positive. So here we'll see the right hand current flow theory, which utilize the right hand rule, and the order convention electricity is considered to be flow from positive to negative in case of current flow theory, and in case of electron flow theory, I consider electricity to flow from negative to positive. Now, important things here, the two methods of determining the flow of electricity should not become confusing. They both result in magnetic field showing in the same direction, because we know either electron flow or either current flow. Doesn't matter for us, because magnetic field is always perpendicular to direction of flow. Hmm. And doesn't matter if electron flowing from positive to negative or current flowing, sorry, if electron flowing from negative to positive or current flowing from positive to negative. Now look here. This is the scale. This is the coil here. This is the coil and current flowing from here, according to right hand rule, from positive to negative. So see, this current is flowing in circular direction. Magnetic field is longitudinal direction. So in second stage, you can see here electron flow theory. Now here current is flowing negative, but current direction is circular. So again here we are getting longitudinal magnetic field. So here doesn't matter how is either current flowing or electron flowing from positive to negative. But here the thing is that direction of current or electron, the field will depends upon that. Generally, it is perpendicular to current flow or perpendicular to electron flow. So magnetic field is always perpendicular to electron flow or current flow. So metal properties we already going to discuss here, and some of the we discussed previously. The following properties of metal can be determined how effective the magnetic particle method will be in evaluating part. Because suppose if you are applying current and the magnetic field is generated with huge amount, but once you remove the current, there is less magnetic field. So that will affect the indications. uh, so we have to see this detailed study about that property, and we are going to see here permeability. Now, permeability, this refers to the age with which a magnetic flux is established in the article being inspected. In here, I will explain in a simple way. If suppose if you are applying the current, the magnetic field will be generated easily. If permeability is high. If permeability is low, even if you are trying magnetized, it will not easily magnetize. Now reluctance, this is the opposition of magnetic material to establishment of magnetic flux. A material with high permeability we have will have a low reluctance. This is the opposition, means we are trying to magnetize the job. You are applying current, but it is not easily magnetized. Means there is resistance to magnetization, and that is known as reluctance. If permeability is high, then material will be easily magnetized. Then in that case, reluctance will be low. Now, residual magnetism refers to the amount of magnetism retained after magnetizing force is removed. Now, just consider you are you applied current. While current is flowing, magnetic field is high. Now, once you remove the current, if you stopped the current, there is some field remaining in the job, that is known as residual field. And the residual field, amount of residual fields depends upon the retentivity of job. If retentivity of job is high, then more residual field. If retentivity of job is less, then less residual field. Retentivity means the ability of material to retain a certain amount of residual magnetic field. Residual magnetism or magnetic field both are same. Now, coercive force there refers to the reverse magnetizing force necessary to remove residual magnetism from the part. Now, if suppose residual field is less, then less reverse magnetizing force is required to remove the magnetic field, and that reverse magnetizing force is known as coercive force. Now here is one of the example here, metal properties. A piece of high carbon steel were placed in magnetized field, it it would exhibit the following. It would have low permeability because it would be hard to magnetize, because high carbon steel means low permeability, and low permeability means it's difficult to magnetize, hard to magnetize. It would be highly reluctant to accept a magnetic flux because of high carbon content. If carbon content is high, then it will not easily accept the magnetic field. It would have high residual magnetic field, but once it is accepted, then it will not it will not allow to leave magnetic field as well. The high carbon steel is reluctant. The high carbon steel is reluctant to accept magnetic flux, but is also reluctant to give it up once it has been accepted. Once accepted, it would not easily leaving the magnetic field, means it will not allow to leave the magnetic field. So it would be highly retentive of magnetic field that has accepted, means retentivity is high. So if retentivity is high, then ultimately residual field will be high, and it would take high coercive force to remove the residual magnetism from the high carbon steel. So if for example here, high carbon steel means low permeability. Low permeability means high reluctance and high retentivity, as well as high residual magnetic field, as well as is necessary. If high residual field means we have to apply more reverse magnetizing force, that means high coercive force. Now, okay. So if you have any doubts regarding this, you can write us, or you can contact us through our mail IDs, or go through our YouTube channels and you can subscribe. Okay, so here our mail ID is given here, iindtpune@gmail.com, and also there is phone numbers. Or thank you very much.